Welcome to today's class. Before we get started, just throwing out a couple of things. Porter? Porter?
Yes, sir.
All right. So talk to me now. What's the standard voltage at which we generate electricity here in Jamaica? What's the standard voltage? Huh?
110 volts.
All right. Mr. Campbell, Conroy, what's the standard voltage at which we generate electricity?
13.8 to 24 kilovolts.
In Jamaica?
13.8.
13.8, good. So Watson? Nikolai Watson?
Yes, I'm hearing you, sir.
What are the transmission voltages here on the island?
69 kilovolts.
Voltages?
Yes, sir, and 138.
Okay, thank you. Was that Turner?
Yes, sir.
What voltage we distribute that? What's the standard distribution voltage? So Turner? We only have
Yes,
to be
sir.
here. What's the standard distribution voltage?
Distribution, that is the 24, sir. 24.
I know why you ask me questions, I want an answer. Huh?
And
So Mason, that's the standard distribution voltage here on the island.
69 kV, sir.
Pardon me?
69 kV.
Christian, what's the standard distribution voltage here on the island?
220, 110.
Pardon me?
220, 110, sir.
I can't hear you clearly.
Sir, I said 220, 110.
Yeah, Mr. Johnson.
24 kV for the line voltage and the phase voltage is
So it's 24
13.1.
kV. That's the standard voltage. All right. So Freda, how do we go about naming steam plants?
By virtue of the fuel it use, sir.
Okay, so give me the name of some steam plants.
Gas turbine.
No, sir. Steam plant, that's it. You tell me about turbine. So Perkins, give me the name of some steam plants.
All right, so good afternoon, everyone.
Afternoon.
So coal-fired plants.
Yes.
We have diesel generators. All right,
steam?
diesel-operated
For
plants.
steam?
Oh no, not for steam. My apologies. Nuclear power plants.
All right. Okay. You have biomass, biogas. All right. And of course, bunker C. We do use that. All right, Mr. Allen, Mario, talk to us about the line models. What are the three types of lines we have in terms of the models. Alan? I did warn you all last week that you know, come put up your name and disappear. Now, I am going to remove you from the room. So I'm assuming that no response means that you're not here. Mr. Allen,
Yes, sir. Good afternoon.
line models. Mr. Allen, we're waiting on an answer. We only have 2 hours for the class. Can't wait all day. So hope.
Yes, sir.
Line models.
I'm driving. You talk like in terms of transmission line and so on and so forth, sir.
Line models, Mr. Hope. What answer is that you don't know, you know? So Bruce, what are the line models?
Yes, sir. Good afternoon.
Afternoon, sir.
Sir, we have short, medium, and long.
Thank you very much. And we determine them by their length. Do you remember the length offhand?
I think for the short transmission line, you have, in terms of kilometers, you have 80 kilometers, shorter than 80.
Very good. Or 50 miles.
For the medium, you have, I think is between 80 and 240 kilometers.
Very good. Or 150.
And for the long lines, it's longer than 240 kilometers.
Thank you very much, sir. All right, folks. It is very unhealthy for you to come to my class without reviewing previous notes. All right. Miss Edwards.
Yes, sir.
Talk to me about the difference in terms of capacitance and inductance for your line vis-a-vis your cable.
It's different.
I need to repeat?
Yes, sir.
Compare for me capacitance and inductance for lines vis-a-vis cables.
Don't understand.
Pardon?
I don't understand.
Okay, Mr. Darby, you can help her.
Repeat question.
Cables versus lines. Talk to me about the capacitance and inductance for these two.
Cables versus the cables are underground, so they have what do I call it? Let me explain it. The insulation for the in terms of the capacitance, it is, I don't remember the name of the insulator, but it is closely packed in terms of the for the cables because it runs underground and the lines are overhead, those that run on the poles.
Okay. All right. So for the cables, the capacitance will be much higher relative to its inductance, and it's the reverse for your lines. For your lines, the inductance is much higher relative to the capacitance. Thank you, sir. All right, students, sounds like some of you have done some reading, and that's good. I encourage you to continue because we build every time you come to my class, you'll be building on what you did the class before. So there's no time for you to, just put on the notes and move on. Okay? While we're at it, however, Mr. Buchanan, you carry?
Yes, sir.
Talk to me now about per unit. Tell me what you know about per unit system. Why is per unit important? And how does it help us?
I'm not sure, sir.
Not sure. Tandel and Sanjay, we need your last names. Correct that and come back. Ahmad, Kimani?
Yes, sir.
Yeah, talk to us about the importance of per unit.
Oh, we use per unit in our circuits because when you have transformers in the circuit, the current on either side of the coils of the transformer would be different. So you'd use the per unit current in the system in order to make it easier when you're building like the equivalent circuit for your assessment of the circuit.
All right, fair enough. But I'll add to that. Well, you're correct. It helps us in treating with transformers, given the different voltages on either side. So for your your per unit current on either side will be different. I mean, your current on either side of the transformer will be different, but the per unit current will be the same. In other words, regardless of which side of the transformer you look at, the reactance, the per unit reactance will remain the same. So that's the key benefit. Mr. King. Christopher?
Yes, sir, I'm here.
Talk to us about the selection. Which two values do you need to select when dealing with per unit?
All right, sir, you need the actual value and the one that is given.
That's calculating the per unit, but I'm saying which values do you, before you do your calculations, which values do you need to select?
Values. You're talking in terms of the
remember, note the word I'm using, select. What values do you need to select? Anybody?
Sir, the base
Sir, you
value.
need the S value.
The
S
base
value,
values.
yeah.
Thank you very much. All right. Okay. And how do we go about selecting the base? Which base values do we need to select?
Voltage base values.
Voltage base and?
power.
S base.
S base. Okay. So, Mr. Bruce, how do we go about selecting the S base?
Sir, I think it is based on the value of the transformer.
What do I add to that? How do we go about selecting S base? Yes, Mr. Johnson.
Yes, sir. There's no rule to selecting S base or V base other than you choose a value that is easy for you to work with.
All right. Well, there's actually a rule per se for the V base, but for S base, it's arbitrarily selected. That's the bottom line. All right. But you're correct. While it's arbitrary, we seek to use values that will make our calculations much simpler. All right. So having gone through that little revision, we can now get started with today. No lessons for today. So let me just back up a bit. So some of this we looked at last time. Talk about the base MVA, the base volts. And of course, we mentioned the fact that for your base values, they can either be the three-phase values, line to line in the case of the voltage, or we can use the line to neutral voltage. However, whichever one we use, we have to be consistent with that throughout our calculation. So generally speaking, we tend to stick with the three-phase value. All right. Because most of the information that you would have been given, for example, with your equipment, would be based on the three-phase value. So we spoke about the V base that is designated in kilovolts, and of course the S base in MVA. And this is primarily based on the fact that that's the system that we're using, meaning a power system, we are talking about kilovolts and we are talking about megavolt amperes. All right. So you will find situations where the system that you're analyzing will be based on volts and kVA. That's possible, but generally speaking, it's in kV and MVA. All right, so we're picking it up now from where we left off last time. So if we have a three-phase and line-to-line base values of 30 MVA and 120 kilovolts, and the actual values that we have, 108 and 18 megawatts. What would be the per unit? Yes, for the per unit voltage, let's give me a minute here. For your per unit voltage, all right, we'd have 108 over 120, and for your per unit power, we'd have our 18 over 30. Now, right away, I know that some questions will be asked about this, where we have 18 megawatts, but yet I'm using the base of 30 MVA and I'm making this unitless. All right? I know that's a legitimate question that can be asked, and we'll talk about it in a few minutes. So in terms of per unit, it's just actual divided by the base that you would have selected. Okay? Now, if we were to look at it from a single phase perspective, we know that for a power of 18 megawatts, then the single phase would be 18 over 3. And of course, for the 108 kilovolts, the single phase would be 108 over root 3. Yes? So we have those values. The base values would be the three phase, 120 over root 3, which gives us 69.2. And of course, the S base would now be 30 over 3, which is 10 MVA. If, of course, we then find the phase values for the actual that I had given. Remember, the actual was 108 and 18. We would have 62.3 and 18 over 3. And of course, obviously, since we're going to be making these, moving from three phase to single phase, we'll be dividing by root 3 or 3. So what it means, therefore, students, is that the per unit values would also be the same. So if you were to find the per unit for the voltage, just divide 62.3 by 69.2, you get 0.9. And if you were to divide 6 by 10, you get 0.6, which is exactly what we had before. So that's the point we're trying to make. So whether you are using the three phase or the single phase values, the per unit will remain the same. But I again remind you that if you are going to be using the single phase, it must be used throughout. You can't use single phase at one point and then three phase at the next point. All right? But generally speaking, we just use the three phase throughout. So we made this point last week. We're just using this simple example to prove that it is so. Any questions? All right, now, I just mentioned the fact that we had a base value of 30 MVA, but I also spoke of 18 megawatts as being the actual, yes? So I'm going to now speak to some conventions that must be applied in doing per unit. All right, we have already established that the S base, you select that arbitrarily. We know that we select the kilovolts depending on where we are in the network, etc., etc., etc. So what I'm going to do in the next 5 minutes, if you don't understand it, you will never be able to do per unit. So pay attention and take your notes. All right, don't rely on getting this video. Take your notes, write them down. So let's go. So we're now looking on the principles that makes the per unit system valid. Yes? So the validity of the per unit system is based on what I'm about to say. First one is that the S base that you select will be used as the Q base and as the P base. So S base is equal to Q base is equal to P base. But what you will select is S base. So if you select S base as 100 MVA, then if you're converting actual power, you would divide it by 100. If you're converting reactive power, you would divide it by 100. Do I make myself clear?
Could you repeat that again, please, sir?
So in other words, that means that the unit doesn't make a big difference then, it's just the value.
Whatever you select for S base, if you're converting P, which is active, or Q, which is reactive, you divide it by the S base. So even though we said before that the actual and the base quantities will always have the same units, even though we said that, I am now saying to you, we're now updating it and saying for your S base, it is equal to P, it is equal to Q. All right? Now remember, we're dealing with, although we said you could also use single phase and three phase, we also said that, yes? However, if you have S base, it means that you can find what we call derived quantities, because once I have S and V, if I have S and V, I can find I and I can find Z. So your base current is therefore given by S base over √3 times V base. So your S base, what you select, yes, divided by √3 times your V base, which you also select, gives you your I base. So earlier, when I asked about the importance of per unit, and we were saying that the per unit current would be the same passing through your transformer. The I base on either side of the transformer will be different. The per unit current will be the same, but the I base will be different. Hence, you can then find what the actual current is on either side of the transformer. But don't worry, don't stretch your mind too much just yet. We'll see how that works in a few minutes.
I'm sorry.
Yes, Mr. Fredo.
Typically, that is for a single phase. I base equal S base divided by √3 times V base, and not necessarily for a three-phase system.
You tell me, Mr. Fredo. Mr. Fredo. All right? Because you all did machines one, right? Okay. So the first statement we made is that P base must be equal to Q base must be equal to S base. And then you can derive I base from that. All right. Next. Z base must be equal to R base must be equal to X base. So in other words, remember you would have selected S and V. From that, you would derive I base, but you can also derive R base. Yes? So R base, or Z base rather, would be equal to V base squared over S base. So a lot of what we are talking about here, students, will be coming directly from your networks 1 and 2. Or in other words, based on what we have here, Z base is also equal to V base over I base. So whichever you prefer. So in other words, when we have calculated Z base, if you are converting resistance or reactance, you would use the same Z base. But remember, Z base would be a derived quantity. There are only 2 quantities that you're going to select, V and S. Everything else is derived. So Z is derived. And finally, do you have this? Finally, Y base must be equal to G base must be equal to B base. So your admittance would be equal to your susceptance would be equal to your conductance, and they are simply, and it is simply given by 1 over your Z base. So you would have calculated Z base, but it will immediately give you the values for your Y base, B base, and G base. All right, so 1 over Z would give you Y. All right. So we have these mathematical relationships, students. We have the one for P. We can derive I base. We have derived Z base, and we know the relationship between Z, B, and G. What I'm saying, Z, R, and X. Now we have Y being equal to B, being equal to G. There is another convention that we have to note. The other thing we need to note all right. Now I may have hinted at it, but now I'm going to be more explicit. And that is that your S base is the same for the entire power system that you're looking at. So whatever base, whatever value you choose for S, it is used across the entire system. So if you choose S base as 100, regardless of the component that you're dealing with, regardless of where it is located within the network, it's the same 100 S base, which is why, and you would have seen this if you have started if you have gone through that tutorial for your lab, it will talk about system base. So you'll have a system base, but you'll also have rating, right? So you'll have the rating of the equipment rating, but you'll also have the system base. So in other words, I can bring a 30 MVA transformer and I plug it into a system that has a 100 system base. And we're gonna talk about how we're going to treat with that to ensure that our calculations remain simple. All right? So the first convention is that SBS is the same throughout the entire system. Secondly, the ratio of the voltage bases on either side of the transformer is selected to be the same as the ratio of the transformer voltage ratings. Now that may sound confusing, but write it down. You soon see how easy it is. All right. What do we mean by this? First, SBS is the same, and then we are saying that the voltage ratio or the ratio of the base voltages must be equal to the turns ratio or the same as the turns ratio of the transformer. Simply put, VBS1 over VBS2 must be equal to V1 over V2, which would be equal to the turns ratio. Let me try and simplify this. What we are saying here, students, is that when I select, remember, there are only two values that we're going to select. We're going to select the base voltage and the base MVA, okay? What this is saying to us is that when we select the base voltage, it must be selected at a point in the network. So it is selected at a certain point in the network. Once I cross a transformer, then the base voltage is going to change. Let me start again. I'm going to select the voltage, the base voltage at a certain point. Yes? Once I encounter a transformer and go across the transformer, the base voltage will change. How will it change? Based on this. So if we're moving from base 1 to base 2, it must be in the same ratio as the turns ratio of the transformer that I am dealing with or that I have encountered. I hope I haven't muddied the water even more. But usually when you get muddy water, you get a filter and you try and clean it up. So let's try and clean it up with a question. Everybody have this?
Yes, sir.
I take this example for me. Okay, so we have our transformer. We have the rating 150 and we have the voltage on either side. The leakage reactance of the transformer, and note that that is measured in ohms, yes? Referred to the 2.3 kV winding. In other words, on the low voltage side of the transformer, when I measure the actual leakage impedance, I am seeing 0.12 at 78.13 degrees, okay? And that is in ohms, so that's an actual value. And I want to now use these values that I have, these ratings that I have, to determine the per unit looking from the high voltage side as well as the low voltage side. So since we have the value from the low voltage side, let's start with that one, eh? All right. So based on the ratings, I'm going to use the ratings of the transformer as the base values. And we can do that because remember, SBS is arbitrary. And the restrictions that I have where the transformer is concerned is that, when I'm crossing, I use the same rating. So since it's just a single transformer, there's no point in using different values. So we have it at 150 kVA. Base 1 is 13.8 and base 2, 2300. So if I start with the low voltage winding, Z base would be equal to V squared over S. Yes? Excuse me. Which gives me 2300 over 150K. That gives us 35.267. So in terms of the base value, base impedance, 35 ohms. Mr. Duncan, how do I find the per unit from this?
Sir, you divide the actual value given the question by this base.
Excellent. So we have actual over base. So the actual was 0.12 at an angle of 78.13. We divide that by 35.267. And we get 0.0034. And I mean, the phase angle remains the same. Now, question. If I went to the high voltage side and was looking at the same leakage reactance, would I get the same value? So if I'm looking on the high voltage side, do I get the same value? Yes, Mr. Grant?
No, sir, you would not get the same value.
Okay, so how will that value change? How would the 0.12 change?
Based on the actual impedance on that side.
Yeah, then I ask you, how will it change? There must be a way.
By the ratio of the
By the ratio of the turn.
There.
By the ratio of the
By the ratio.
Yeah.
Not totally correct. Anybody? Anybody else? Go again.
Squared.
By the square of the turns ratio.
By the impedance.
So if we go to the high voltage side, yes, then the leakage impedance would now be equal to N1 over N2 squared times Z2. And from that, it will be 4.32. Of course, the angle doesn't change because it's the same relationship in terms of inductance to resistance. All right? And by the way, this 78, this angle of 78 is one that you will use in several areas in power systems and power system protection. Excuse me, don't worry, I'm in the room alone. And that was a genuine sinus issue.
All right, sir.
Thankfully, we are not in that air-conditioned room at 182. But anyway. All right. So Z1 is 4.32. So that's the actual impedance on the high voltage side. So now I need to find the base impedance on the high voltage side. So question, what would be the S base on the high voltage side?
The same 100.
Same 150K. Good. I'm just checking to see if you're following. So the Z base on the high voltage side would be your V base squared over your S base. So it gives me 1269.6. And if I find the per unit on that side would therefore be equal to the leakage reactance, yes, which is 4.32 over the 1269, which gives me 0.0034, which, ladies and gentlemen, tells us that the per unit, regardless of the winding that I am looking at, so whether I am coming towards from the high voltage end, the per unit reactance of the transformer will be 0.0034. If I was coming from the low voltage end, it will be the same. So in other words, the transformer in per unit would be reduced to a single reactance value, which is the same regardless of the direction we're coming from. And this is the power of per unit.
So that I can say, so the transformer is reduced to a single value.
It has a single per unit value, regardless of the winding that I'm looking at it from.
Okay.
So keep in mind, let us not miss the point. The same transformer, if I look at it from the high voltage end, the reactance is 4.3. The actual impedance will be 4.3. If I go to the low voltage end, the same transformer, the actual will be 0.12. However, in per unit, whether I'm going from high or low, it will be 0.0034. Yes, Mr. Clark.
Okay, sir. Afternoon. Good afternoon, sir.
Yeah, speak up. You're allowed me to.
Yeah, so you're saying, sir, whether the transformer is delta on one side and star on the other side, the per unit is the same, just the same.
Matters not.
That's not.
Matters not.
Okay, sir.
Good. So we're just going to run some theory now. A lot of what we have said so far, we're going to repeat it, but this is just repeating using some derivation so that you can actually make, if you forget it during an exam, but really and truly, we start with per unit. Your first labs will have a lot of per unit conversion. So, by week 5, you're per unit experts. So there's nothing that you're going to really forget. But, we have to ensure that we teach what's on the syllabus. So this shows an ideal single phase transformer. Note what we are saying here. An ideal here would also mean that there's no voltage drop. So E1 per unit would be equal to E2 per unit. I1 PU is equal to I2 PU. So the per unit from winding 1, per unit current from winding 1 through to winding 2 would be the same. The per unit voltage on winding 1 would be equal to the per unit voltage on winding 2. And we want to prove that. Okay. So let's start with the actual values. So we start with the actual values. Wow, it's almost 5 already. Okay, so with the actual values, we know that E1 over E2 is equal to N1 over N2. All right, nothing spectacular. Which means that E1 is equal to N1 over N2 times E2. Now, if I want to find the per unit voltage for winding 1, then I would divide it by the base voltage. All right, so I would divide through by the base voltage. So remember what we said earlier, that when we select the base voltage, we select it at a point in the network. Yeah? So it's at a point. So VBS1, unwinding 1, we'll find the E1 per unit, which is given by that expression. So, of course, we'll be dividing the right-hand side of the equation also by VB1. So, Mr. Forrester, what is the convention we said needed to be applied when we're dealing with base voltages? What convention we said needed to be applied? Look back at your notes, because I'm sure you wrote it down.
When dealing with base voltages.
Go again? The convention for base voltages.
S base equal Q base equal P base, sir.
No, man, voltages. What's the convention? We said that needs to be applied for voltages, base voltages.
Must be selected at that point.
The ratio of the voltage on either side.
The ratio must be the same as the turns ratio for the.
Yeah, man. Yes, man. So by convention, VB1 over VB2 is equal to V1 over V2 is equal to N1 over N2. So right away, based on this convention, we can substitute for N1 over N2. And if we substitute for N1 over N2, which would be equal to VB1 over VB2, yes, we're going to be left with, do we have this?
No,
Yes.
sir.
All right. So if I make that substitution, all right, we'll have that, we'll be left with E2 over VB2, which we know is E2. So it means that E1 per unit is equal to E2 per unit. So I've proven that. But we can do the same thing with respect to the current. To show that I1 base, I1 per unit, sorry, would be equal to I2 per unit. Okay. Now, earlier, I said that S base will be the same right across the system. I also mentioned that it is on that basis that we talk about system base, right? But when you buy a transformer from a manufacturer, that transformer will come with a certain rating. So it will come with a certain MVA rating. Right? And whilst we did not talk about it, in your machines, you would have done power factor correction and them things. You remember those things? And in part of that discussion, I would imagine that you would have talked about the fact that the utility company will rate its equipment based on the MVA rating. So when they try,
correct.
When we try to put up small businesses in residential communities, we are wreaking havoc on the power system. And we think the utility just wants to know what is happening in order to increase charges. But it's not so. It's just based on the fact that, we're rating it on MVA. And of course, the lower the power factor, you need more MVA to produce or to supply the amount of megawatts. All right? All of that fancy jazz. Why am I telling you all of this? Because when you purchase that transformer and you're now going to install it in a network, and you're going to do your calculations, the manufacturer is not making the transformer just for your network. So he's going to give you the ratings of the transformer, whether the reactance, the MVA rating, you name it. He's going to give it to you based on the unit itself. So we talk about nameplate rating. What it is that the piece of equipment you're purchasing is rated at. But when you put it in that system, you need now to do some calculations. You want to be able to use the system rating to carry out your calculations. And that's what we are going to be looking at. How do I convert from rating per unit on rating to per unit, to system per unit? That's what we're going to talk about right now. So we start by talking about change of base. And this is what I just said. The nameplate rating of a component are normally, note I put it here, are normally used as the base values. So that is what the manufacturer will give you. So when you get a transformer and it is rated at 0.1 per unit, that 0.1 per unit reactance is based on the nameplate values. Meaning, if it's a 30 MVA transformer and you have the base voltages, or the voltages, the turns ratio, the voltage ratio, sorry, it is those values that are used to dictate or give you the per unit reactance. All right? But you put it in a system and you don't need to convert. Let's see how we go about doing that. So let's start first with, if I'm trying to find new per unit, then this would be my formula, because per unit is actual over base. But what is the actual? Although I have the per unit values, let me just go back up to the question that we just did. In this question, the actual from the high voltage winding was 4.32. You with me? The actual from the low voltage winding was 0.12. Yes? So the actual value, I mean, it's there, whether or not we're looking from one side or the other. However, what remains consistent is the per unit. But the actual, whether I measure it from one side or the other, that value will remain. Okay? So coming back to change of base. This actual value is going to be equal to the per unit, the one that I have, times the base that I had. So the actual would be equal to the old per unit times the old base that I had used. That won't change. So the actual value remains the same. So if the actual value remains the same, if that remains the same, then it is equal to Z per unit old times Z base old, which is what we have here. Also? So it means therefore that the Z per unit new, students, I mean, we can write it a bit better than that so that it helps us to remember. All right? We can write it a little better. So this would be equal to Z old times Z base old over Z base new. So the new per unit value would be the old times the old base over the new base. And the old per unit times the old base is just giving us the actual. So that makes our calculations quite simple. But so Wilson, how do we find Z base? Is Z base a derived quantity?
Yes, sir.
Hey, so how do we find it?
So you can, it depends what is given, sir. V base
What is
square
given?
over S base, sir.
Go again, Mr. Forrester.
V base square over S base.
Thank you very much.
V base over R base.
All right, that's a given, Mr. Wilson. So it means that we can substitute for Z base old in terms of the voltage on S. And that's a substitution. So the new per unit, and this formula, students, this is your first midnight formula for power systems. Oh, you don't know what midnight formulas are? Midnight formulas are those formulas, if I wake you up at midnight from deep sleep, you must be able to repeat it. All right, so this is your first power systems midnight formula. All right, now we may not necessarily use this at this time. I'm trying to recall. Oh yes, you do. Coming up in one of your labs, you're going to use this. I'll just show you how we go about calculating it. Are we finished with this?
Yes, sir.
Yes, sir.
All right, cool. I'm giving you this. The main focus is really this. And this is usually considered at your bus bar. And what you have down here, that is known as the MVA short circuit level. So the SCL there means short circuit level. In many instances, you may not necessarily need to calculate this. What the programs that you will be exposed to, or for power systems, the program that you will be exposed to will do the calculations for you. So you'll get the short circuit level at the bus. And what this says to, what this gives you is it gives you an indication as to the maximum current that the bus bar can handle without being destroyed. All right. Just to give you a final formula in terms of changing base. State the sum, please. So ZPO1 per unit impedance 1 equals Z times S base over V1 squared, which is going to be the same as Z over Z base. All right, but we're using multiply, so multiply by the reciprocal. And ZPO2 now from equation 1, I write an expression for Z. So it means that I just take this over, all right? And then substitute it into equation 2. So I'm making Z the subject from equation 1, and then I substitute it into equation 2. Then I'm going to get something that's a little messy, but don't worry, it cleans up after a while. So making the substitution for Z, so from equation 1, make Z the subject, and then it substitutes in equation 2, I get this. It looks very messy, but simply put, this is our final equation. So this is your general equation with respect to changing base. Really, I should have had B1 and B2 for the voltages. So if you wish, you can just correct that, put in the B1 and B2. But generally, it wouldn't change anything because we know that V1 over V2 would be equal to VB1 over VB2. All right? Admittedly, I try not to remember these things, but if you have a challenge remembering it, just remember that you start with a new base, S base. And once you have the new at the top, everything falls into place. All right, so it's now 5:09. Go to Schoology. I don't know how many of you have access to it as yet, but log into Schoology. The question I'm going to go through, or the questions that we're going to go through, I put all 3 of them on the platform, so you can access it now. So you won't spend time going through in terms of writing them down. All right. So we can just go through the solution.
Sir.
Yes, Mr. Freighter.
Yeah, I've completed the 10 step and sent a request to be accepted in
Freighter, I
Schoology.
responded to you. You have sent a request to join Schoology 3 times. I accepted the first one. You sent a second one. I delete it. You send a third one. I delete it. You are already in Schoology, Mr. Freighter. And I wrote to you advising you that you are already there. So stop sending me the requests.
Well, there must be something wrong on my side because I'm not seeing anything inside there. So
I'm sorry, sir, but I accepted the first one. Do you want me to delete the first one and you send me again? Since you like to send these requests, but I accepted it. Is there anybody else who have not been able to access Schoology? Is there anybody else in the room who hasn't been able to access Schoology?
I have not accepted. That's it.
You were not accepted? Mr. Bruce? Mr. Bruce? You sent
yes,
a
sir.
request and you were not accepted? Is that what you're
No,
saying?
I did not send a. No, sir, I did not send a request.
Is there anyone who sent a request to me for Schoology who has not been able to access the platform? All right. So there's your answer, Mr. Freighter. I don't know what else to do.
Sir, what can we do at this time? Should
I
you
just
delete
said
that?
it to you, sir. I will delete you from the group and you make another request. I have, let me see now. I have, I think, 47 or 49 students currently in Schoology who have sent in their requests and I have accepted them. You are one of them. So I don't know what else to do. But anyway, here's the question. And note, it's coming from a textbook. So if you don't catch it now, you can go back and look at what I'm doing. But I will try to break it down. So this is your network, students. Oh, by the way, did I say we don't have anything else to talk about in terms of per unit? If I didn't, then that is it. We have nothing else to say. What we're now going to do is look at some questions and make sure that you solidify your understanding of the principles. Okay? So from the question, it's there in your in Schoology, right? What we have here, you would have a bus bar here, you would have a bus bar here, you have a bus bar there, you have a bus bar there. All right. Now, because this is your first example, we have shown 3 zones. So we have sectionalized the network into 3 sections. Why? Because when you move from this point, let me not say this point. That's 1, 2, 3, 4. All right. So I move from bus bar 1 to bus bar 2. Yes, moving from bus bar 1 to bus bar 2. What would I have done, Mr. Ferrer? What have I done moving from 1 to 2? Mr. Ferrer?
Yes, sir. Yes, sir.
Mr. Ferrer, I'm moving from bus bar 1 to 2. What have I done? Child Mason, what have I done? Sir Mason?
Yes, sir. I just came back. My internet went off. You hear me,
All right.
sir?
Go on the line.
Not hearing it properly, sir.
Mr. King, moving from bus 1 to bus 2. What have I done? Apart from move from bus 1 to 2.
So you cut across the transformer?
Beautiful. The fact that I have gone across a transformer, what is that saying to you about the base voltages? Mr. King, we're not done it, man.
Not okay.
What will happen to the base voltages?
So the ratio would be the same as the ratio of the turn.
Okay, so in other words, the base voltages would change.
Yeah.
Okay, now, where you going, Mr. King? Me tell you, close your mic, man.
No, I'm just mute until they ask me the question, man. I'm here.
All right, so, Mr. King, you see, because you did that, I forgot the question I was going to ask you, and it was a beautiful question. But anyway, my word, this is getting serious. All right, you get to Mr. King, because I forgot the question. But anyway, we're going across the transformer, which means I move from zone 1, which would have a particular base voltage, going across over to bus bar 2, I then have a new base voltage, which is why we are saying it's in a new zone. So the same base voltage would exist between here. Yes? And then I'll have a different base voltage over this side, which I now call zone 3. So students, although we have been saying we started discussing per unit that S-base is arbitrary, because you wouldn't expect me to give you a question and allow you to arbitrarily select it. I would have 50 different questions to mark, and I'm sure you don't want to put me through that stress. All right? So in the question, you are now being told that you're going to use base values of 30 kVA and 240 volts in zone 1. Because remember we said you have to specify the point in the network that you're taking the base voltage. All right? So in this instance, we are specifying that the base voltage is 240 volts at zone 1. So that's the question. All right, we're just going to jump into the solution because, as I said, the question is already in Schoology and you can access it later on. All right, and then finally, we want to calculate the load current in both per unit and in amperes. So let us go. So students, we're trying to find, the objective here is to draw the per unit circuit and determine the per unit impedances and the per unit source voltage. So the first thing I want to do is to draw the network for which I'm going to find all of these values. And the network would be the same thing that we had in the question. To be the same thing. However, we'll replace each component, yes, by a reactance or a resistance. Is that understood? Is there anybody who don't understand what I just said? We're going to replace each component with a reactance or resistance. All right.
Sir.
Yes, Mr. Wilson.
So would it be safer to say impedance rather than resistance?
Let me just say that. What did I say? Tell me exactly what I said.
You said reactance or resistance.
What's wrong with that? Absolutely
Well,
It's
nothing is
perfectly
wrong, sir.
correct.
Yes,
So let us
yes.
move on. All right. So let us start with our source. And we know if we draw a source. So that's our source. All right. All right. Tell you what. Let me use black. All right. So we have our source, and of course, it is Earth. Now, from the network that we have, we were not given a reactance value for the source. All right. So we're not given a reactance value for the source. However, you can be given one. But in this instance, you're not. So let's move on. So we have our source, and from our source, we then move to bus bar 1. And between bus bar 1, we have a reactance. And this reactance would represent what?
The
Are
first
you guys
transformer.
looking at the circuit? You have it?
First
Have you accessed
transformer,
Schoology?
First transformer zone 1.
All right, so we have T1. All right, and then after T1, we have the line. And then we come to bus bar 3. And from that, we have our transformer again. Yes? And then from that, we have our load. And from our load, so in a sense, the network that I've drawn here, when we find all these reactances and resistance, what would it represent? Come on, man, talk to me. What would it represent? What would you have when you have found all of these reactances and resistance?
One line diagram.
It's a one-line diagram, but I mean, look at the circuit, what do you have?
Sorry, the system impedance.
Huh?
Would it be
Actually,
a
calculating in
System
transmission.
impedance.
per, would it be
Yeah,
a
Mr.
per
Williams?
unit, would it be a per unit circuit?
Yes, it's a per unit circuit, but when I find all of these, what will I end up with?
Impedance.
Answer. Reactance and resistance.
The leakage resistance?
You know, I think I have too many good students. You know, you are too bright for your own good, or maybe my questioning techniques are just so horrible. What you would have is a simple series circuit. That's all I'm asking. You have a source, and you have some reactances. Because remember, these 2 points are Earth, so to go back around. That's all.
Sir, that's too simple. We didn't think that's so.
Yeah, that's what I say. When you're too bright, that's a problem. It's a simple series circuit. And if you have a series circuit, I would imagine that being successful in networks 1 and 2, you can find the current and everything else, right? So this is how our life is made simple, gentlemen. So the question now is, how do I go about finding these per unit values? So we have T1. We have T2, and then we have the load. I'd use LO for the load. All right? So we can start with the generator. Again, have you accessed the question on Schoology as yet?
Yes, sir. Yes, sir. We're looking at
All right. So what is the actual, first of all, we are told that the base voltage in zone 1 is 240. Yes? So what would be the per per unit voltage for the source. So for the source, VPU will that be equal to?
220 at angle 0
divided by 2.
divided by the 240.
So we have 220 over 240. And what's that equal to?
.9167.
You have done your first per unit calculation. All right, now for T1. For T1. For transformer 1.
Sir Isaac, question.
Yes.
The angle wouldn't be important back in the answer?
Yeah, sure.
Okay.
Sure. But I do have bad habits from time to time.
Okay.
Okay. So for T1, what are the ratings you have on T1? What's the ratings you have on T1?
30 kVA, sir.
30 kVA. So for T1, S equal 30 kVA.
240.
I have 240 volts.
It's 240. I'm sure that's not what you have. 240 what?
240 per arm by 480.
240, 480.
Can't tell that at 8 or 2, sir.
Huh?
In my thing, I can't tell if it's 8 or 2.
Okay, well, 240, 480. What else you have there?
The impedance, I can't tell which impedance. Reactance, I mean.
So you have a 0.01 per unit reactance.
Reactance.
0.01?
0.10, sorry.
0.1. You know, let me double check. 0.1. Oops. All right, and you have X to be equal to 0.1 per unit. All right, so that's for T1. Now we have put T1 in the system. And as we said, if we were changing, because it's now in the system and we have a system base, etc., etc. Now, let me make it abundantly clear that nothing is going to change for T1. However, I'm going through the process because this is what you would do for all transformers. But with time, you will recognize that some values will not change, all right? So I'm telling you that before it happens, so you don't think it's, we're just wasting time. All right, so for T1, we want to find Z new. So Z new would be equal to Z old into, what we say we started? S new. So, so once you have S new, it's S new over S old times V old over V new all squared. Everybody with me?
Yes, sir.
So the ratings that you have for T1, would be based on rating. So the per unit value you have here is based on rating. So that the values on the transformer would be the old values. The new values are the ones that you are now applying from the system. All right? So in this instance, for T1, you would have Z new would be equal to 0.1 times 30K over 30K times 240 over 240 squared, which obviously will give you 0.1 per unit. About it, man?
Yes, sir. So when you go on the other side of the transformer, that's when this is going to take real effect, basically. The other transformer.
If I went to the other side, Mr. Wilson.
No, I mean the other transformer, the transformer T2.
Hold on, Mr. Wilson. Make we take it one step at a time, man. May I ask if you understand what on the slide? Make we deal with this one. Good. Yeah, Mr. Johnson. I keep telling you, Wilson, not 3 years, no, me I want, stop running ahead of me, man.
Hello?
Yes, Mr. Johnson.
I feel like we know the answer to the question already, but seeing that we know that the base is, like the base wouldn't change, this step would be, you could just write about the 0.10 and move on, or do you still need
But but remember what I said, Johnson. You guys have to listen carefully, I said to you, I am doing it because this is what you would normally do. However, with time, you would recognize that it would not change. You would have come through this before you decided to drop me last time or drop the module, right?
Yes, sir.
So it is out of your experience why you know that. The rest of the class is coming to it quite fresh. And I am saying to them, you take this approach. With experience, you will recognize that it would not change. But for now, you don't have the experience, so you do what I have done. All right? Okay. So that's for T1. So XT1 per unit. All right? So I can now go back to my network, and I know that this is 0.1. All right. Next. Now, after I pass the transformer, what's the next component we have?
The line, sir.
The line, beautiful. Now, how will I determine what the base voltage will be on the line? What is the line connected to?
Transformer 1.
Transformer. Good. So how will I determine, yes, what the base voltage will be on the line?
With the same base voltage as for the transformer.
Sir, 480.
Go again? Go again? I didn't hear that.
Sir, it's on the 480 side of the channel.
Yeah, but how do I determine what the base voltage is?
So you'd have used the turns ratio with the
Thank you very
original.
much. So in zone 2, so we know say for zone 2, let us VB2 over VB1 is equal to V2 over V1, where V2 and V1 would be the turns ratio of the transformer. Everybody with me? So V2, what's V2 for the transformer? Read?
480, sir.
480. So 480 over 240. Yes. And what was VB1? What was the base voltage in zone 1?
$240.
240. So it implies that VB2 is equal to 480. Students, it looks as if I'm just repeating some things that, we already know, but just take my foolish advice. It is not as simple, all right? So let us get into the practice of writing out these formulae until we have gotten to the point where we're a lot more comfortable. Okay. So what do I now need to calculate in zone 2? Because remember, for the line, what do I have? What do I have for what information do we have for the line?
The actual reactance.
Actual reactance. So I need to find the per unit. So what do I need?
The base, sir.
This base. And Z base in zone 2 would be equal to, how do I find base voltage?
The S square over V.
No, sir.
V square over base, sir.
V squared over S.
Sorry.
So that would give us 480 squared over 30K. Work that out, please.
$7.68.
So I have 7.68 ohms. So Z per unit for the line would be equal to 2 over 7.68. What is that equal to? Wow. Time is running.
Um, 0.26042. 26042.
All right. So I can now go back up to my diagram. And put in the per unit for the line. Okay, so I now come to the second transformer, and for the second transformer, we have 0.1510, sorry. And that's on rating, right? So we want to find the new per unit value for the transformer. So for T2, so for transformer T2, what is the, and listen carefully, on rating, yes, on rating, what is Z base? For the for T2, on rating.
0.1.
Z, well, oh Jesus, I'm sorry. My mistake. On rating for your transformer, what is V base? Sorry, not Z base.
460, sir.
460. All right. So we want now for transformer Z new. So tell me what I'm going to write. I'm not writing any formula. I just want you to give me the numbers.
That'll be V or 480 divided by.
All right. So what were you saying?
0.1, sir.
Huh?
0.1 times.
0.1. First thing. Times. Which one I say you must start with?
New one, sir. The new
S new.
S new. So what is S new?
20 kVA, sir.
No. Remember.
480, sir.
No, listen, don't guess. for the transformer, what is the KVA rating?
20 kVA.
20 kVA.
20.
Right, sir.
What is the system KVA that I'm now using?
30, sir.
30. So what's the new KVA?
30.
30. So you start with 30.
Road.
And the old is what it was. So it will be over 20.
Okay, sir.
All right. So remember I said earlier that, you know, we were repeating the things we knew it wouldn't change. So Mr. Johnson, that's why I'm saying, let's go through this. With time, you will start to appreciate the differences. Okay, so in terms of the voltage now, so we start with S new. So over here we'll have V old. What is the old?
460.
We have 460. And what's the new?
480.
480.
480. And what do we do now?
Square that, sir.
Square this. So we have 0.1 times 30 over 20. I mean, the K's will cancel, so we don't need to put that in. We have 460 over 480 squared. And what does that equal to?
So 0.13776.
All right. All right, you can see that. 0.13776, all right? Now, students, just for the benefit of completeness, if I had looked on transformer 2 from the other side, yes? So if I had looked at it from the low voltage side, what would be the base voltage in zone 3?
Would it be the 115?
No, listen, the base voltage. Remember the base voltage?
120?
120. 120. Because remember, the ratio of the base voltages must be the same as the turns ratio of the transformer. Never forget that. All right? At the risk of sounding sacrilegious, that is, you know, that's per unit gospel. All right? So, if it's 120, it means that if you were looking at it from the other side, this voltage ratio that you have here would be 115 over 120 all squared, coming from the other side. You with me? And if you did that, I mean, the 30 and the 20 would remain the same. So the 115 over 120 all squared times that, times 0.1, would give you the same result. Point I am making is that the per unit reactance, regardless of the side of the transformer you look at, would be the same. So this is just reiterating or reinforcing what we said earlier. Everybody see with me?
So I'm kind of zone out right there, sir. Explain how you get the 120 again, please.
480 over 460 must be equal to x over 115. Work out x.
Okay.
Did I say 120? Yes. So 460 or 480 over 460 would be equal to x over 115. All right. And then we now come to the load. What information will I need for the load? What do we have for the load, students?
We have the actual value, sir.
So what do I need?
The base, sir.
Huh?
Base, the base.
Base. And how do we find the base impedance? What is Z base on the load side?
V square over S
V
base,
square
sir.
over S. S
And
base.
what is V base on that side?
120, sir.
We just,
One-
yes.
one.
So it's 120 squared over 30K. All right? But that gives us
0.48.
0.48. So the per unit for my load, so for the load, we'd have, what was it again? 0.9 plus J 0.2 divided by 0.48. What does that give us?
$1.875
Plus J
plus
0.
0.41667 G.
All right. So you can now stick that into the, so I have 1.875, 0.41, whatever. All right. And then you simplify. And what you now have is that so this is 1.875. And you add up all the reactances. All right.
Excuse me, sir.
Yes.
Sir, my internet went out at the point, the part where you had the new base, sir, where you were getting the new impedance. Not the new, yes. Where you said that the 30K over the 30K, which is you get the Z new, sorry. That's the first one that you had, where we got the 0.10 per unit. I was actually wondering why did you use the 30 over the 30, sir, and the 240 over the 240 square.
All right. Check back the recording because I've gone over that twice already. So check the recording later.
All right, sir.
All right. We're running out of time, which is why I'm suggesting that. All right.
Yes, sir.
All right. Cool. Okay. So what is the total reactance? Okay, so I'll leave you to work out. Whatever the total is, which is just adding up all the reactances that you had. All right, so you have 0.316 plus the 0.4, so that's 0.7, 0.8, it's about 0.9.
Yes, sir. It is 0.91485.
$91485?
Yes, sir.
Okay, so from this, students, you can find your per unit current. So this is at angle 0. Yes, and we're finding IPU. So the per unit current throughout the network would be the same. In this instance, because it's a series connection. Yeah?
So we can go to the slide before that, please.
Anything you missed, just go back to the recording. We're running out of time right now. We are up to 10 minutes to 6. So you calculate the per unit current. Whatever you get for the per unit current, it will be the same current through all the network. Okay? What you will now need to do in finding the actual current in any part of the network is to find the base current. And remember, the base current is dependent, yes, on V and S. All right? So, basically, so let me just divide up the network. So the base current here would be different from the base current here, would be different from the base current on this side. So this would be a zone 3, this would be a zone 2, and this would be a zone 1. So remember, if you want to find the current going into the transformer, you would use the base current on zone 1, in zone 1. Same per unit value, but you use the base current in that zone. For zone 2, that would give you the current leaving the transformer on the 480 volt winding. But it also gives you the current through the line. And it will also give you the current going into the 460 volt winding on the transformer. And then for the 115 volt winding, you would find the base current in zone 3, using, of course, the V base, which would be 120, not the 115, 120. And from that, you'll find the currents right through the network. And that's it really for per unit current. But I'm worrying because there are a couple questions that are in the document I sent you. There are a couple of things I may just want to mention. So you have the network, and remember, I've put in all these transformers. Yes, it's gonna give you some work to do, but after you have, practiced enough, going across transformers, it will become nothing after a while. Somebody asked the question earlier, good question. Doesn't matter whether you're dealing with star or delta, or star delta, yeah? Doesn't matter. In the question, just note, I've given you, for the transformers, I've noted them in percent, right? 15% and 12% simply means 0.15 per unit and 0.12, because percent simply means out of 100, all right? So for those two, it is 15, it is 0.15 and 0.12. And for the other question, and of course, you note I have given you various MVA values. Again, this is not to make your life difficult. What I'm doing here is to force you to do repetitive actions so that it will become commonplace to you. All right? And also for the third question, all right, let's just take a little calculation. I'm giving you the reactance per kilometer. And instead of giving you a value, I'm giving you the length of the line. Okay? So really and truly, for this one, note that we're specifying that you're using 20 kV at the motor. So here's the motor. All right? So the base kV is 20 kV at that point. All right, so it means that you now have to expand in terms of going across transformers and noting the base voltages. So these two questions I'm giving to your students. And this is your first assignment from Power Systems. All right, and as part of your first assignment, you will have until 9 p.m. on Friday to submit this. All right, so you'll have until 9 to submit this. What else do I need to say to you? So that's your first assignment for submission. And for your first reading assignment, you're going to be looking at the key operational features of transmission lines. That is in chapter 4 of your text. All right, and those operational features you will find it useful for your first couple of labs. All right. So that is it, except for the fact that I have not yet taken today's register, which I am about to do. All righty. Please listen to your names. I will call you no more than twice. Alan, Romario.
Yes, sir.
Alan. Alman.
Yes, sir.
Bailey. Bailey. Brown, Gareth.
Yes, sir.
Buchanan.
Yes, sir.
Bosu.
Present, sir.
Kamak.
Here, sir.
Ms. Kamak, you accuse me of not giving you access to the module. Next time, make sure that you're accessing Power Systems and not networks, okay? You were given access.
Sir, yes, sir. I saw that I was given access.
Campbell. Conroy.
Yes, sir. Yes, sir.
Chambers.
Present, sir.
Chen.
Here, sir.
Clark.
Here, sir.
Bailey.
Yes, sir.
Darby.
Here, sir.
Duncan.
Present, sir.
Edwards.
Here, sir.
Ferguson. Ferran.
Yes, sir.
Ferran.
Yes, sir.
Forrester.
Yes, sir.
Freighter.
Here.
Grant.
Yes, sir.
Gray.
Here, sir.
Paul.
Yes, sir.
Harvey. Harvey. George Henry.
Yes, sir.
George Henry.
Here, sir.
Zavina.
Yeah.
Zavina
sir.
Henry. Miss Henry.
Present, sir.
Miss Henry, I'm going to ask you to stay on the line after the class, okay?
Yes, sir.
Pope.
Yes, sir.
Johnson.
Yes, sir.
King.
Yes, sir.
Lynch.
Present, sir.
Mason.
Here, sir.
Merchant.
Yes, sir.
Morrison. Mundell.
Here, sir.
Perkins.
Here, sir.
Porter. Tyreek. Porter.
Yes, sir.
Ready. Reed, Christoph.
Present.
Rose, Colin. Shand. Thomas, Bonai.
Here, sir.
Joel, Turner.
Here, sir.
Watson.
Here, sir.
Danikia Watson. Wilby, Williams, Wilson, Richardo. All right, so that's
Here,
it.
sir.
Richardo, that's you?
No, sir, Wilson.
Don't mark carry, man. What's your problem? All right, that's it for today.
All right, sir.
All right, have a good evening.
Okay,
Mr.
so
Henry, Mr. Henry, remain online.
Yes, sir.
sir.
Sir Isaacs.